Electrical conductivity in conductors. To generate a conduction current, electric charges must move along a path. These charges can be positive, negative, or both. To set the charges in motion, an electric field must be applied. When an electric field is applied, for example from left to right, by convention, the field direction points from positive to negative charge. Naturally, negative charges move opposite to the field direction, while positive charges move along the direction of the field. In this case, the motion of charge can result in a conduction current. For example, consider a piece of wire, specifically a copper conductor. At normal temperature, there is a high density of free electric charge, negative charge. But under normal condition, the motion of these charges is random and disorderly. We can say that the rate of which charge enters and exits any cross-section of the conducting material is equal, and as a result, this motion does not produce a net current. However, if an electric field is applied across the two ends of this wire, that is, if a potential difference is applied, creating a field E, then the field exerts a force on the free charge that is stronger than the Coulomb force between the charges themselves. As a result, the free negative charge in the conductor move in an ordered manner. Now consider cross-section of the conductor, its area denoted by S. During a time interval del t, a charge del q passes through this cross-section. We can therefore define the current I as I equals to del q divided by del t. And in this case, a current is generated. However, different materials vary in terms of the amount of free electric charge they contain. To examine this, let's take a brief look at the atomic structure of materials. According to the simple Bohr model, an atom consists of a nucleus containing neutrons and positively charged protons, shown here in red in the diagram of the atomic nucleus. Electrons occupy discrete shells surrounding the nucleus. For example, in a copper atom, the first shell contains 2 electrons, the second shell contains 8 electrons, the third shell contains 18 electrons, and finally the outermost shell contains 1 electron. Under normal conditions, the amount of positive and negative charge is equal and the atom is electrically neutral. The farther an electron is located from the nucleus, the weaker its attachment to nucleus becomes, and the less energy is required to separate the electron from the nucleus. The outermost discrete shell surrounding the nucleus is called the valence shell, and the electrons in this shell are called valence electrons. Under identical conditions, the energy required to free a valence electron differs across different elements. The energy required for an electron to break free from the valence shell and move into the conduction band, which is what actually enables the generation of electric current, is called the band gap energy, usually denoted as E sub G. In conductors, at normal temperature, E sub G is close to zero, extremely negligible. Therefore, electrons are easily freed from the valence shell and reach the conduction band. This is why conductors have a very high density of free electrons per unit volume at normal temperature. As discussed, In conductors at normal temperature, a large number of free electrons are exist per unit volume. As a numerical benchmark for conductors like copper, if we consider a volume of 1 cubic centimeter, that is a cube with sides of 1 centimeter, the number of these free electrons is on the order of 10 to the power of 23. However, at normal temperature and in the absence of an external field, the motion of these electrons is random and disordered. Therefore, practically speaking, no current is generated across any hypothetical cross-section, since the number of electrons entering and exiting is approximately equal. So, in the absence of a field, despite in the presence of a large number of free charges, there is no current. However, when a potential difference is applied across the two ends of a conductor, the electrons experience a force from the field in the direction opposite to the field, and they begin to move. In this case, if we consider a cross-section, a quantity of charge delta Q passes through that cross-section during a time interval delta T, generating a current. This motion results in a velocity, that is, the charge begin moving at a center velocity under the influence of the force exerted by the field. The velocity is called the drift velocity, given by v sub d is equal to mu sub e multiplied by e, where mu sub e is a coefficient called the electron mobility. Now, for conductors under an electric field E, let's isolate a differential volume element, a volume delta V, with length delta L and cross-sectional area delta S. Naturally, delta V equals to delta S times delta L. This is the volume of the differential element we have selected. We know that per unit volume of the conductor, the number of free charge is, say, n. Within the selected volume delta V, the number of free charges is obtained as n delta V. So, the number of free charge within this differential volume is n delta V, since each of these charges carries the elementary charge E. The charges delta Q equals to Ne delta V. Now the current is delta Q divided by delta T. We have calculated delta Q. Delta T is the time required for this charge to travel the distance delta L and path through the cross-section delta S. So delta T equals the distance traveled delta L divided by the drift velocity V sub D. Naturally, we can substitute this in, and after simplification, the current is obtained as I equals to NeV sub D delta S. Current density is defined as the amount of current passing per unit area. So, we obtain the ratio I divided by delta S from this relation. J equals to NeV sub D. And since we know that the drift velocity V sub D equals the electron mobility multiplied by the electric field intensity, substituting gives us J equals to n e mu subs e e, which we set equal to sigma e. So, we define the coefficient sigma, which the value n e mu sub e, and call it the specific conductivity, whose unit is Siemens per meter or mho per meter. Now, we look at current density from a vector perspective. Current density actually indicates the direction of current flow. Current is conventionally defined as positive to the direction of electron motion, or equivalently in the direction of positive charge motion. We can assign current density a direction along the field direction. So, vector J is equals to sigma times vector E.